Now, the graph of quadratic expressions can also help us talk about the range of a given quadratic expression. Recall that from what we had discussed, the range of a function refers to the set of values that the dependent variable will assume as the independent variable is given all its values over the domain, right? So we'll take two possibilities over here. The first case, of course, is that if A happens to be positive, right? Now, if A happens to be positive, we've already seen that the graph will be a parabola opening up, right? So maybe let's say something like this is the situation. So in talking about the range of the function, the vertex now starts playing an important role. So the vertex again over here would have been minus b by 2a comma minus d by, which in this case is this specific value, let's say. Of course, it doesn't have to be strictly this. The vertex would have been anyway. We're just taking an example. Now the idea again is that, let's say the range, the domain of this function of course is all real numbers, so and because the parabola expands on both sides to infinity. So from minus infinity, so the question again is that as x varies from minus infinity to infinity and you keep a track of how y is changing, what are the set of values that y will assume. So now if you visualize this idea, you know that maybe through a value x you've drawn a line parallel to the y-axis and that intersects it at some point p, suppose. So clearly, from what we discussed, the y coordinate of the point P will give us the value of y, right? So now it's easy to visualize that as x varies from minus infinity to minus b by 2a, the y value will come from infinity to minus d by 4a along the y-axis, right? And then as x varies from minus b by 2a to infinity, y will again start from minus d by 4a and go back all the way up to infinity. So what has effectively happened is that y has assumed all values between this minimum value of minus d by 4a and it goes up till infinity. There is no upper limit, right? So in that sense, I can now say that for any quadratic expression in which the coefficient of x square is positive, assuming that the input takes values from minus infinity to infinity, the output will have a minimum value of minus d by 4a. That minimum value itself occurs at the vertex at x equal to minus b by 2a. The minimum value is minus d by 4a, and there is no maximum value. There is no upper limit. It will go all the way up till infinity, right? So the range effectively becomes the set of values from minus d by 4a all the way up to infinity. So again, assuming that a is positive, right? So min f of x over here denotes the minimum value of f of x, and as we've seen that they will not be a maximum value as such. It goes up till you can keep increasing the value of y by keeping on increasing x, or for that matter decreasing x. So therefore the range of f of x is the interval minus d by 4a, where d again is a discriminant, right? So as an example, if y is, let's say, x square plus x plus 1, right? So the discriminant over here is 1 minus 4 minus 3. So the range will be that y will assume its minimum value in this case, because it's again a parabola opening up. That minimum value will be minus d by 4, which is 3 by 4, and it will go all the way up till. This is assuming that the independent variable x takes all values from minus infinity to infinity. Similarly, in the case when a is negative, in case of a being negative, we've already seen that we'll get a parabola opening down. So what will happen now is that the function, maybe, so let's say, just for the sake of discussion, suppose the y-axis is somewhere over here. Right, so what we can now again say is that as x varies from minus infinity to infinity, the y value will come from minus infinity and it will reach minus d by 4a at the vertex, minus b by 2a, and then again start decreasing parallel. Right? So in this case, minus d by 4a represents the maximum value that the function assumes. That value is still assumed again at minus b by 2a only. So I can say that the range of f of x is the set minus infinity to. Right? So in this case, again, for a parabola opening down, you will have a maximum value at x equal to minus b by 2, and the value, and that value turns out to be, that maximum value turns out to be minus d by 4a, and therefore the range can be thought of as minus infinity to minus d by 4a. Right? So again, as an example, if you have something like, right, so for the function represented by minus x squared plus 2x plus 1, the range will be minus infinity to 2. And again, it is important to note that these results that of the ranges are necessarily valid only if you know for sure that the input is assuming all values between minus infinity to infinity. A trickier problem could be to find the range of a quadratic expression under a restricted domain. So for example, if the question is that you want to find the domain of this function, let's say over the interval 2 to infinity, or maybe over the interval 0 to 2, then in that case the answer will not necessarily be the same. In such problems, you'll have to resort to basic ideas and you'll have to go to the graph of the function. Right, so all these questions are based on the range of a quadratic expression. Although in the first and second question, you don't exactly have quadratic. So obviously, this overall function is not a quadratic expression. It is overall an exponential. It is a composition of an exponential function and a quadratic expression. But still, we'll be able to figure out the range. So first, let's try to figure out the range of this part. So x square plus 8x plus 17. What can we say about this range? So again, if this is y, so the discriminant is how much? 64 minus 68. So that is minus 4. So minus d by 4a becomes 4 by 4, which is 1. So that is effectively saying that y is greater than or equal to 1. Right? Call this entire expression and denoted by the variable u. So u obviously becomes 3 raised to y. So now what you can simply say is that since y will be greater than or equal to 1, 3 raised to y itself will be greater than or equal to 3 raised to 1. So that gives us that u, the variable u, which was denoting this entire expression, will take values which are greater than or equal to 3, and therefore the minimum value of this expression as x takes values from minus infinity to infinity must be 3, right? So if I want to find the range of values of u, I'll need the range of values of the variable y, and for y again, the discriminant is 1 minus 8, so that's minus 7. So minus d by 4a becomes 7 by 8. So y is therefore greater than or equal to 7 by 8. Which obviously then also means that it is positive, so I can reciprocate both sides and the sign of inequality will reverse, and I can multiply by 14 on both sides. The sign of inequality will remain the same. Yeah, 14 by y is the variable u, and this of course gives you 16. So again, as x varies from minus infinity to infinity, y will vary from 7 by 8 to infinity, and therefore u will have a maximum value of 16, and of course the lower limit will be 0. Clearly this expression is always going to be positive. Right? So the maximum value of this expression therefore is 16. The last question is an ID problem. It's relatively straightforward. So for this function, the discriminant again would be, suppose d1 would be 4b square minus. Right. So the minimum value of f of x should be d1 by 4. So that will be b square minus. Similarly, for the function g of x, the discriminant must be 4c square plus 4b square, and a is of course minus 1. Right? So the maximum value of g of x should therefore be minus of d2 by minus of 4. So that will again be c square plus b square. So as per the given condition, b square minus let's just check the signs once again. X square plus 2bx plus 2c square, and g of x, so the discriminant should be 4b square minus 8c square. Oh, sorry. So we had to divide this by minus 4, so I'll get minus b square plus 2c square. Okay. So the given condition is that minus b square plus 2c square is greater than c square plus b square. That gives me the condition that c square must be greater than b square. So in the fourth question, we've been given that x and y are these two real values which are bounded by this relation, that x plus 2y is always equal to 1. And under that condition, we want to find the maximum possible value of x into y. So suppose you keep on taking, you'll have infinite ordered pairs x comma y will satisfy this condition. And if you keep calculating for each of those ordered pairs the value of x into y, it's turning out there is a maximum possible value of x into y. And you want to figure that out. And we also want to figure out the value of x and y for which that maximum value is u. Right? So the way we could proceed in this question is to again, suppose we designate xy by some other variable z. Right, so over here, z, the variable z has a dependence on two variables x and y. But here, x and y are not independent variables. They themselves depend on each other through this relation. So let's try to eliminate any one of the variables. So let's maybe eliminate x. So instead of x, I'll get So finally, we have the situation in which we are saying that the variable z depends on the variable y, and this is the dependence, right? Now this clearly makes z a quadratic expression in terms of the variable y. So as y takes all possible real values, from what we already discussed, z itself will assume a certain maximum value, which is given by minus d by 4. So the discriminant over here again will be 1, and of course the constant term is 0, and so minus d by 4 becomes 1 by 8. Right? So 1 by 8 therefore is the maximum possible value that this expression will assume, which then is also the maximum possible value that z assumes. So the max value of z. As far as the second part is concerned, you want to find the value of x and y to which this itself happens. That again now becomes fairly straightforward, because we already discussed that the maximum value will occur at the vertex. So for max value, y should be minus b by 2a. So that will be minus 1 by 2 times minus 2. So that is 1 by 4. And once I know y is 1 by 4, I can substitute over here and get the value of x. So x will turn out to be 1 by 2. Right, so that's our final analysis. The maximum possible value of the expression x into y is 1 by 8, which happens when x is half and y is 1 by 4. You could have also at this stage, instead of reducing z to a quadratic expression in terms of y, you could also have reduced z as a quadratic expression in x. You would have got the same set of answers, obviously. Another interesting application of quadratic inequalities is to find the range of some specific kind of rational functions. Now, a rational function is a general category of functions which is defined as being any function which is basically expressible as a ratio of two polynomial functions. So maybe something like 2x minus 1 upon x plus 2. This is the ratio of a linear function and another linear function. So this is a rational function. Similarly, you could have had 2x minus 1 upon x square plus x plus 2. This is of the form linear biquadratic or cubic biquadratic or fourth degree biquadratic and so on. So basically a rational function is a function, any function which is expressible as a ratio of two polynomials. So for three specific kind of polynomials, linear biquadratic, quadratic bilinear and quadratic biquadratic, we can use the idea of quadratic inequalities to find the range of such functions, assuming that right. So L by QB basically means a linear function by quadratic, quadratic by linear, quadratic by quadratic. So over here we are assuming that the numerator and denominator do not have a common factor. For all the three forms, the idea is pretty simple. So let's take an example. We'll try to understand the whole process through an example. Or let's talk about the whole thing in general forms. So maybe for q by q, we'll discuss it for q by q. So maybe this is your So this is specifically for the q by q form, but it's applicable to the other two forms also. And again, we're assuming that there is no common factor, right, on both sides. So you shouldn't have a situation where there's something like x minus 1 into x minus 2 upon x minus 1 into x minus 3 or something like that. Right? So over here, the first step would be that I'll cross multiply and rearrange terms and write the whole thing. I'll get all the terms to one side by cross multiplication and write that entire expression as a quadratic in the variable x. Right. So cross multiply, rearrange, write as a quadratic in the variable x. So when you do that, you'll get something like this: x square we'll now basically use the logic that since we are talking about a real function, x obviously is a real and y also has to be real. So we will kind of look at the whole situation in an opposite way. So we'll say that we only find those values of y. To find the range, we effectively want to look for those values of y for which the corresponding values of x will turn out to be real. So for example, if I take y as, let's say I give y a certain value. Maybe for y equal to 2, you get a quadratic. For a specific value of y, you get a quadratic in the variable x. If solving that quadratic gives you non-real roots, that effectively means that that particular value of y that you started out with cannot be assumed by this function. X will have to take a non-real value to be able to assume that value, which of course we don't want to allow, right? So we'll essentially just use the logic that I just want to consider those values of y for which this expression will have the corresponding real values of x, which means that the roots of this equation must be real, and for that to happen, we already know the discriminant should be greater than or equal to 0. So in the second step, we'll just impose the condition that the discriminant, the b square minus 4ac value is greater than or equal to 0. That will now actually give us a quadratic inequality in the variable y, and the solution of that quadratic inequality will be the required, will give us the required range. Right, so it's a pretty basic, it's a pretty fairly easy steps to follow. So we'll just apply it to a couple of problems and see. Right, so let's start by applying the idea to these two problems. They're similar, both are quadratic by quadratic form. Again, as I said, it could have been linear by quadratic or quadratic by linear form also. So for the first one, again, let's start by calling this expression as y. So again, in the next step, I'll cross multiply and rearrange terms. So I'll get something like this. In the next step, we say that we'll impose the condition that the discriminant must be greater than or equal to 0. So that gives us 9 into y plus 1 whole square minus 16 to y minus 1 whole square. You can expand it also, but you can factorize it also. So in this case, this is 3y plus 3 square minus. So I'll get something like 7y minus 1 into 7 minus y is greater than or equal to 0. So it's again a product of linear factors form. I can use the wavy curve method, but the coefficient of y over here is negative and over here it's positive, so I'll multiply by minus 1 throughout. So that becomes the same. And now again by your wavy curve method, 1 by 7, 7. So the solution set is. So we're saying that the set of values of y has to lie between 1 by 7 and 7, which then is the range of this function. So therefore this expression, this entire expression lies between 1 by 7 and 7. So the minimum value is 1 by 7 and the maximum value is 7. Let's quickly apply it to the second problem also, second part. Cross multiplying and rearranging. Finally reduce my inequality to this form, y square plus y. I'm dividing by minus 2 throughout. So, but then again I'll have to reverse the sign of inequality. Dividing or multiplying by a negative number. When you multiply and divide both sides of an inequality by a negative number, you have to remember to change the sign of the inequality. So again, it's getting factorized quite easily. Right? So again, for this to be less than or equal to 0 by the wavy curve method, so that's what we get. Y has to lie between minus 5 to